Hi, how's it going? My name is William Billows, and I will be looking at the constant velocity of an expo marker. And so the purpose of this lab is to compare the position of an expo marker moving at a constant velocity to the predicted position using a computational model from GlowScript. So the principles we will be using is Newton's second law with the momentum principle, and that states that the net force is equal to a change in momentum over a change in time. And so exploring the momentum principle, we have F net equals delta P over delta T. And we can substitute P equals mv into the equation momentum final equals momentum initial plus the F net multiplied by the change in time. And so we can turn this into the velocity update, which is the final velocity equals the initial velocity plus F net over the mass multiplied by a change in time. And so the observed position, we can see here in our experiment a video of the expo marker. And so when we graph this, we have the x position versus time. We will be ignoring the change in the y coordinates because it is almost negligible. And we can see here that we have a upward facing slope. And here we have the coordinates of the time and the x position. And so we can take this into our experimental graph, and we will be comparing this to the computational graph. So we have a computational model code, and we have set up our initial boundary conditions with the initial velocity vector ignoring the change in y. And I found this by finding the average change in velocity. And I found the initial position through tracker by comparing the position of the expo marker to a 1 meter stick. And so the initial time is 0, and delta t is 0.0333 because that corresponds to the frame rate of the tracker video. I also set the net force to 0 because at a constant velocity there is no net force. And there's no mass here because the mass will not affect the position as F net is equal to 0. And so what the position update code is going to do is accurately predict the movement of the expo marker. However, it is a little limited because we are only taking into account the x-axis and not y. And just to show the computational model code here. And so when we set up a computational graph, we have the code position x versus time, and the slope is 0.401 at 8x plus the intercept, which is 0.1699. And during our observed graph, we have 0.3896x plus 0.2466. So we can see here that there is a slight deviance between the computational and the observed graph, but it is similar enough to say that there is only a small statistical error. So the reason that we have this computational error, first of all, is because there's no change in y. We have rounding errors of the constant average velocity. There could have been issues with tracker, and additionally there's human error with the center of mass tracking. I could have accidentally messed it up by a couple of units in the computer, and so there's no way to actually see if it's going to be 100% correct. So what if the plus x and negative x coordinates were changed? The slope of the graph would be negative, but the absolute slope would still be the same, showing that the results would not be completely changed. So was F net actually 0? No, because the computational model deviates from the actual model. So there were some slight forces at play, such as friction, but they are negligible because they make such a small difference between the code and the actual experimental graph. Thank you so much.